Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 25 on Multivariate Analysis of Variance, or MANOVA. And just like Univariate Analysis of Variance, or ANOVA, this is a method for comparing means between groups. So we will download the Markdown file and the data file. This is a data file that you've used before, and I need to refresh this page. There we go. Oh, you know what? Never mind. I apologize. There's a technical reason why that link doesn't work at the time of recording this video, and I think we'll just ignore that. I'm just downloading the data. Classes 23 onward all use this Razorback sucker fish data set. Anyway, so we've opened up the assignment. We'll set the working directory as the source file location and knit the file. There is a G-Galley pairs plot in this assignment, which will take a little while to plot. While that happens, let's review the assignment on the website. So it's the Razorback sucker data we've got for 4 groups of fish. We have their stable isotope ratios, and we want to know whether the means of the stable isotope ratios are different between these species of fish. So we have 5 sources. We have 2 from the hatchery, 2 from the wild, and an unknown. We're going to exclude the unknown fish for the purpose of this assignment. And our goal is to test whether the known source populations have different multivariate means, and if so, which pairs differ. So it's just like ANOVA, where we do the omnibus hypothesis of are all the means equal, or is at least one pair different? And if we reject the null, then we do follow-up post hoc tests to ask which pairs differ. All right, so we read the data set in, and well, let's just start here. Looking at the scatter plot matrix below, clean and or transform the data if you think it'll be helpful. Note that measurement error can be an issue in complicated biological measurements. Furthermore, transformation might help separate observations that are tightly grouped in space. Furthermore, one of the model assumptions of MANOVA is that you have a multivariate normal distribution for your data. So we'll do our best to satisfy all of those requirements by looking at the plot of the data. All right. So we library the tidyverse, we pull in some functions. In this case, the function we're going to be using from here is the multivariate normality visual test. Okay, so we read the data set in, it's got 1,500 observations. After you remove missing values, we're down to 1,450 roughly. And we are also going to exclude the unknown sources. And we're going to retain the source column, that means which group the fish are in, and as well as the columns with the isotope ratios. So the resulting data set has a source and 2, 4, 6, 8, 9 isotope ratios. We have 4 elements, and we have 2 of barium, calcium, magnesium, and strontium, I believe, are the 4 that are here. I'm not a chemist, so it's likely I got at least one of those wrong. If there are modifications to the data set, we will include those modifications in this code chunk here. All right, so the solution is basically the code that we're going to write here. So based on, as I page up for a moment, based on what we see in the scatter plot, we're going to clean and transform, etc. And page down, that's what we're going to put in this code chunk. All right, so let's go see what we've got. I do a G-Galley plot, and colors are going to be the different sources. We have a density plot on the top, points on the bottom, and let's zoom way out to begin, and then we'll probably zoom in to have a sense of what's happening. So we have the sources in the first column; those are the 4 colors. We have barium. These first 2 are highly correlated, and not that correlated with the other isotopes. We have calcium, which is all by itself. There's just one isotope of that. We have magnesium, which are highly correlated within themselves, but not really that correlated with the other elements. And then also strontium, which is highly correlated with itself, but not with the other elements. We definitely see some outliers here. Let's zoom in a bit and get some more information about that. So the purple values here that are really outlying, those are in the calcium, Ca43. Boy, I hope I have that right. I suddenly feel like I need to make sure that I've got some of this correct, and should have done this beforehand. So we have Ca. Yeah, this is a dumb thing to do on calcium. Okay, well let's just assume that I've got it right, and you can anyway, we'll ignore some of my errors if I've named these incorrectly. But the main thing here is that we've got calcium, which has those 2 outliers for the purple source, which is labeled at the bottom and hard to read because the letters are overlapping. Over here, let's see, purple, SJR, San Juan River. Okay, so there are some outliers there. So we should probably consider what is a typical value for calcium as we look at these plots. Definitely say larger than 0.5. The minimum is really sort of around 0.6. So let's be conservative and maybe set a cutoff of 0.5 and above for calcium. All right, so I'm going to go over to the R code and we're going to make this one change, and then we'll recompile the document and see if there's anything else that we should change. All right, so here's the code for the solution. So we've got in fact, we could probably just add it to this San Juan data set here. I guess I'll just put it down here. So we've got dat. Okay, and we want to filter the Ca43 greater than 0.05. And we'll knit that. Okay, so we're going to keep everything greater than 0.05. That's going to make the calcium plots look much nicer. And we'll see if there's anything else that we can improve. Okay, that was pretty good. Didn't take that long. I'm refreshing. Oh, you know what? That's from the this is from the website. Let me open it from the open in browser, the one that we just compiled. I don't like that. Why is it? So our markdown looks like, did it complete? We have a warning message, output created. That looks correct. No, okay, not sure what happened. Calcium 43 greater than 0.5. Okay, this is off my desktop, but the the plot still has those points. Okay, so I'm not quite sure why calcium 43 is the variable name. Keep all the ones that are greater than 0.5. And I'm just double checking the scale down here, 0.5. So what I've done appears to be correct. Let's double check the code for the plot. Oh, you know what's happening? Cache. Okay, so I haven't really talked very much about cache, but cache is a way of not running a piece of code if it hasn't changed to speed the processing of the code. And I should have had a suspicion that that was the case, because when it got to the G-galley code right here, it jumped right past it rather than taking a long time, which is what it's doing now, because it's actually reproducing that plot. So the main idea here is that once we've have the data in the format that we want, and we're happy with, you know, any exclusions like we just made or transformations of the variables, once we're happy, we don't want to have RStudio or R replot this code over and over and over again. So by caching this chunk of code, which is the scatter plot matrix, it doesn't need to replot it unless we sort of start over again, as we just did. So I will restore this cache equals true once we're happy with the result. All right, now let's go look. We refresh, and okay, good, at last. So here's calcium. We look down, and there are still sort of that left tail of values, that there's still a few values out there, but those are all values that are greater than 0.5. So it seems that we probably could trim this a little more carefully if we want to. I'm sure that these 5 points are going to be troublemakers later on. But anyway, let's not go too crazy. We'll leave them in right now. What other patterns do we see that might be problematic? Well, it definitely looks like for barium, these first two columns, like we've got a lot of values that are scrunched up on this lower boundary. Hard to read the scale here to know what that boundary is. It's probably close to 0. And then we've got another one that is really has a wide distribution. Wide distribution here. It seems that if we were to take the logarithm here of these two elements, the bariums, then I think that we would compress the purple and the blue distributions and spread out the other two distributions, the pink and the green, in a way that would be a bit helpful for having equal variance between our groups. So let me try doing that as well. So go back to RStudio, page up for a moment until we've got to the code chunk. And in addition to filtering, let's mutate. And we've got the barium 137. And let's say, how about a log 10 barium 137? And we'll do the same thing for barium 138. And we'll compile this. This will recreate that plot, and we'll see what we think. All right. While that's working, so when we're happy with all this, we're going to describe the relationships between the isotopes of the same element and between different elements, and the source populations may or may not be different. Describe the source differences you see. Okay, so let's summarize what we see once this finishes compiling. Still working on the plot. We do have a fairly large data set. I wouldn't be strongly opposed to having a tighter bound on the calcium. On that lower bound, we had a bound of 0.5 initially, and if we tighten that up, we'd probably remove some of these outliers. Okay, so you can see the jump now that this log transform for barium has made. It's given them more equal spreads along the x-axis. That's going to be very helpful for our multivariate analysis. Also, it's really separated our pink and our green populations. So I think this is probably a helpful change. The only other one I would really consider is considering a tighter bound on the barium, but I'm not going to do that at the moment. So let's make some comments. Describe the relationships you see between the isotopes. So, oh, you know what? Before we do that, we did make these changes, and we wrote this code to address that. We should make some comments in the code to document why we made these decisions. Remove a few low outliers, and maybe here transforming the BA values, and that ends up separating the tight clustering on the boundary, something like that. Okay, back to making some comments about this, and I'll just sort of describe what I see paging down. Relationships between isotopes of the same element. So, like these three are strontium. They are very, very highly correlated. If you have a high isotope ratio for one of the strontiums isotopes, then you tend to have high concentrations of the other strontium isotopes as well. But there doesn't seem to be much correlation between the isotopes, between isotopes of different elements. So I would say those are my primary comments. In terms of the source populations separating, it looks like the red, there's some hope for, oh, look at this, look at these tails off the red too. Looks a bit like a jellyfish. Those are going to be outliers for the red distribution. So we'll probably see that later on. But it looks like we can separate the red from the others. Looks like we can separate the green from the others. But the blue and the purple basically lie on top of each other. So those two are probably not different. So if I was making a prediction at this point for MANOVA, we're probably going to expect to see differences between the red and the green and the others, but not between the blue and the purple. And I would say those are my main summaries for the source population differences. All right, let's get on to the model assumptions. We've got Shapiro-Wilk tests for multivariate normality, and I also wrote a function for effectively sort of like a QQ plot for comparing the Mahalanobis distance, it's a squared distance, sort of d squared, to a chi-square distribution, which is the appropriate distribution for if the data were multivariate normal. Keep in mind that we have large sample sizes, so the numeric tests might be too sensitive. We do expect some deviations for the extreme D2 values, but they should not be too systematic. Okay, and we'll try to address any deviations with transformations if we can. So here is where we get our multivariate normal tests from, and this multivariate Shapiro test, we are doing this for each population. Let's go look at the code for a moment, because the code looks much tidier than the output. Okay, all the output I'm about to show you comes in basically these 8 lines. These first 4 is a multivariate normal test, and what I'm doing is I'm taking the data set, I'm filtering to only include each source separately, and then I'm removing the column, the source column, so that we just have a matrix of numbers. And this test requires the orientation of that matrix to be transposed. so that it sort of goes along rows instead of columns. Anyway, so I do that for each of these, and then we look at the output. And then I'm going to create a plot. This function is one of mine in that ADA functions script. And this is doing using the same code inside. I do a multivariate normal QQ plot. Okay, so that's what we're going to go look at. So here's the first one. Let me zoom out a little bit so it's easier to see. So for the DEX source, looks like the data are not normal. For the next one, not normal. For the next one, not normal. For the last one, not normal. Okay. As I said in my introduction, these numeric hypothesis tests are probably a little too sensitive because of large sample sizes. And they end up being very sensitive to small deviations. Let's look at these QQ plots. This is what I would tend to base my my decisions on. And I'll zoom out one more. Okay, so it looks like, so the second GJH population or source and the NAP sources, those are beautiful. Okay, for DEX and SJR, they are mostly normal, but then there's this tail of, in this case, 2, 4, 6, 8, 10, maybe about 10 values that are, deviate from normality. Same thing over here, 2, 4, 6, 8, 10. It's not that many actually. And this deviation of going up above the line means that these are outliers relative to the normal distribution. Okay, so at this point we have a choice. We could go back to the plot and see what else we can do. For example, there's these purple points. Well, let's see, which populations did I just say? DEX and SJR. Okay, so let me page up. DEX is the red, SJR is the purple. For the red, you can see those troublemakers. It's these down here. So sort of maybe large values of barium for the red group. Now these large values of these large values for the red group are not large relative to the other groups. They're just large in terms of red. So yeah, what would I do if this was my data and I was doing this analysis for real? I would probably, those definitely look strange. I would the first thing I would do is I'd go back to the records of those fish and look at how the data were measured, the analysis through the mass spectrometer, and I would see if there's anything unusual in the sampling or measurement process of these fish. If there's no issue there, then I'll probably just keep them as they are. A third option is to basically create a cutoff for the red group that anything above, let's see if I scroll down a little bit. I can't really read the axis, but you get the idea. Anything above whatever this cutoff is, maybe you exclude that. We still have these, which are, you almost want to do a diagonal and remove the values below there. But anyway, so we're getting into some sophisticated selection at that point. So, but you might consider doing that. Furthermore, for these purple ones, it's probably these outliers way over here. So you could probably create a cutoff which applies to all populations. We already created one cutoff for this variable, who maybe it needs to be in a bit further. But ultimately, like, the best thing to do is go back to your records about measurements and see if there's any unusual properties in those measurements, and if you can discover some irregularities, address it at that level. Anyway, let's keep these observations in. What will these outliers do? They will inflate the variance. They will create a little bit of bias by moving the mean over. So the bias is one of the major problems. The lesser problem is that they inflate the variance. If they inflate the variance, you end up with a weaker test because right, everything has to do with variance. So the larger the variance is, the more uncertainty there is, the less ability to discriminate between the populations. So it may lead to more conservative results in that we may not find differences when there actually are differences. Anyway, I guess I would say that if you had looked at this before we did those transformations, I bet it was worse. Now it's probably better. And there are the two groups on the off diagonal follow the normal distribution very well, but the other two seem to have deviations which represent outliers. Okay, let's perform the multivariate ANOVA test. So first, state the null and alternative hypotheses in words and notation. Then we're going to select the robust test statistic and interpret the result in the context of the data set. All right, let's see where we've got, okay, so here I've got using the car package, and after you fit this linear model, which looks fairly complicated, you put this into the MANOVA function, and it gives you a test result. So yeah, let me describe what's happening here a little bit. Basically, you need to create a linear model object that will then be fit by this multivariate ANOVA. And what we're doing here is the source is the categorical variable. So we've got the four sources for the fish. This cbind puts all of these columns together on the left-hand side like a big matrix and fits that to the source. Now what that actually does, let's go to the R Studio and just run that. I don't really need to run this, but I'm running all code. Oops, let's run everything from the top, including the GG pairs plot. All right, and we'll move down. All right, so we'll run this, and I want to show you the result of this LM_man for MANOVA. I guess while we're waiting here, we are happy with our GG pairs plot. So I am going to put this cache argument back into the code chunk option. So we don't need to create the plot every time after this. All right, so we ran. Oh, I guess we didn't. There we go. So the LM_man object effectively ran a bunch of independent linear regressions, and the coefficients for all of those are here. So we've got basically an ANOVA model, and these are the four coefficients when the response is BA137, and it fit all these individual models. I wonder what happens when we do a summary of that. Do we get output? You bet we do, for every individual model. Okay, so when the response is BA137, this is the resulting ANOVA coefficient with the t-tests for the coefficients. Then, if I scroll down a little bit, we have BA138, and it fit that model. Okay, so this object has all the individual linear regression models, and that's used in the MANOVA to do a multivariate test. The result is highly significant. That there's very strong evidence for, wow, F statistic of 91. There's very strong evidence of differences between the means for our four sources. All right, So what did I ask you to do? State the null and alternative hypotheses in words and notation, select the test statistic, and interpret the result. All right, let's see if I can help you with this. So I would probably go back to the lecture notes for MANOVA for the hypothesis tests. I will try to state them here. So we can let the mean, mu j, where equal the multivariate isotope ratio population mean for the populations. And we've got DEX, GJH, NAP, and SJR, which are numbered. I'll just put this J equals 1, 2, 3, 4, respectively. Okay, you have to put the word respectively because that's what academics do all the time. All right, we wish to test the null hypothesis, so H underscore 0 colon, that mu 1 equals mu 2, which equals mu 3, which equals mu 4, versus the alternative, HA, that text RM not H naught. Okay, that at least one pair is different. At least one pair of means differ. Let's see. I believe in the lecture notes I discuss the number of multivariate tests, and I indicate that the ply is the most robust of the test statistics. There should be, let's see, MANOVA. If we look for the help for this, we must have the ability to select from other tests. Looks like test statistic, likelihood ratio, Wald, F. Looks like there's some other ways of getting that. Okay, but the default, nicely, is the one that we want. Okay, sorry for moving all that around. Okay, so we picked the test, and what did we observe? We could pull out this. There we go. The test statistic probably by looking at the objects inside. Let's see. I think that gives the name. Let's see how else we can get that name. Oh, interesting. Oh, that's really cool. Okay, I sort of forgot about this. If you ask for the summary, you page up for a moment. If you ask for the summary, it gives you a bunch of information, but sort of important for the moment. It gives the 4 different tests that were discussed in the notes with all of their test statistics. So that's pretty good. And if we look for the names of that, we'll probably then be able to get a table. Maybe multivariate tests. Multivariate tests. And what if we just do 1,6? I'm trying to get to that table. Let's see what the names are for the multivariate tests. Just source. Okay. Anyway, I'm having a hard time finding a way to get to, let's see, source. Okay. If you just keep going, right? So we started with the object, then we did the summary of the object. Under there's multivariate tests. Under there's a test for source. And then we get these, we start to get these labels. Maybe P is the one that we want. Let's see. Capital P? Nope. We can unlist. Okay, well, this is becoming not very good for finding a way to access these values. So much for using a fancy way of listing what the p-value is. Sorry for that long detour. I guess there's some value there in that sometimes you can find ways of accessing these values directly, and other times maybe you can't. And it's not to say that you can't. It's printed out, so you must be able to get to it somehow. I just wasn't able to find it very quickly the way I was trying to search for it. Okay, let's draw our conclusion. So we're doing this hypothesis test. Because the p-value is less than 0.05, we reject the null hypothesis in favor of the alternative hypothesis, concluding that at least one pair of sources have different population means. All right. So we've decided that there are differences. So now we go into multiple comparisons to try to discover which pairs differ. And so I give you this code for this nested loop to make comparisons between all pairs. And I think I will take the time to explain what this loop is doing. Let me go do it on the HTML file because it's a little easier to read. All right, so below I wrote nested loops to compare all pairs. Right, so if you have a list of items like this, and you want to do all pairs, it's not very hard to do that if you know how to write a little bit of code. So what I've done here is I started with the data set, I pulled out just the source column, I asked for the unique values, and I sorted them alphabetically. And I put that list into source list, and here they are. So how would you do all pairs? Well, you can pull out pairs of sources in this way. Okay, so you can say, I want the first one and the second one. So that should be DEX and GHJ, GH, and that's what I've got right here. So that's looking good. And so how would you algorithmically work through every pair? So what I would do is I would choose the first one and hold that as the first of the two, and then the second one I would iterate through the other three. So start with 1 for the first one, and then the second one is going to be the second, then the third, then the fourth. Then I select the second one as the first of the two, and then pair it up with the next one and the one after that. And then I select this one and pair it up with the last one, and then I'm done. I've done all 6 pairs. So algorithmically, this is very handy code. This is something that, when I'm iterating through pairs of things, I write this code, every time, basically. So the first, so I want to create pairs like this, 1, 2, in this bracket. And I want to fill in the indices, 1, 2, 1, 3, 1, 4, and then 2, 3, 2, 4, and then 3, 4. Those are all the pairs. So the first index, so the first source, is going to start at 1, and then it's going to go up to the second to last one. Okay? So whatever the length of the source list is, which in this case is 4, that minus 1 is going to be 3. So the first source is going to take the values 1, 2, and 3. Whatever the first one is, the second source is going to be the one after that. Okay, so if I started with 1, then the second source is going to be 2. And it's going to iterate all the way to the last one. The length of the source list is 4. So when this is 1, the second one is going to take values 2, 3, and 4. When it's 2, when the first one is 2, then the second one starts at 2 plus 1, which is 3, and goes to 4. And when I is 3, which is going to be the last one, because it's one fewer than the total list, then the second one is the one after that, 4. And it also ends at 4, because that's the length of the list. Okay, all that's very hard to wave my cursor and try to explain. I do print out a couple blank lines, and then to make sure that things are working correctly, I print out the source number and its name for the comparison that's being made. And having this type of printout for a loop like this is very important, because it will help you confirm that you have done all of this labeling correctly. Let me get a sip of water. Okay, once you've got one of the pairs, okay, let's say the first one, when I1 equals 1 and I2 equals 2, and I've printed that out, then in the car package I'm going to do the MANOVA, and I'm fitting this big long linear regression just as I did, if I scroll up for a moment, in the main ANOVA right here. It's exactly the same code. The only difference is that the data set I'm going to filter to only include the 2 sources that I care about. So I've got my long linear model code, and the data for that linear model is the data set filtered where the source is in the list of those 2 sources that I selected. And then I'm putting that into the MANOVA pair, and I'm going to print out the result. And for some reason in R, when you go around a loop, you need to put a print here in order for the result to be printed. If you just had man pair here without the print, it would go around the loop and you wouldn't get any output. So make sure to print the output when you're inside loops. So here's the result. Let me try to get the code on the screen, at least for the first one. So I've got a couple blank lines, because that's what this does. And then I've got some stars, comparison between number 1 and that source name, 1 DEX, and 2 GJH. So I know which pair this p-value belongs to. So those 2 groups have a small p-value, so there's a difference between those 2 groups. Then it goes to the next one, 1 versus 3. And there's a difference between those 2. Then 1 versus 4. And there's a difference between those 2. So DEX is different from all the other groups. Next. Now the first one increments to number 2, and the second one starts at the next value. 2 versus 3, there's a difference between those 2. 2 versus 4, there's a difference between those 2. Finally, 3 versus 4. So we got to 4 in the second one, so then the first one increments to 3 and 4. Those are the last pair. It's done, and those are not different. So our intuition early on, when we looked at this multivariate plot, came true, or it was supported by the tests supported our intuition that the 2 wild fish, I think that's how we refer to them, the Nappy Ponds and the San Juan River fish, laid on top of each other, and they are not statistically different. Okay, very good. So let's maybe fill out these last couple things here. We've got specify the Bonferroni corrected alpha level for the pairwise tests. So we've got, let's go over to the RStudio and scroll down. Okay, so because there are 6 comparisons, I'm going to use, how about alpha equals 0.05 divided by 6, which equals, and I could write some code here, might as well, R 0.05 divided by 6, and how about we do that to, I don't know, 5 significant digits, maybe 4, as the test level. Okay. Next, which pairs differ? So they all differed except for the 2 wild populations. So I can say, I don't know, DEX different from the others, GJH different from the others, but the 2 wild populations, NAP and SJR, do not differ from each other. Okay, that's a fairly simple way of summarizing those results. Okay, the canonical discriminant functions. So this is really just a way of visualizing the difference. We're going to take the data and we're going to perform a rotation, and we're going to visualize the rotation. And I think I choose, yes, there are 3 canonical functions. We're going to get into this in a later chapter in more detail, but basically we find 3 directions that best illustrate the differences between the groups. So the canonical discriminant analysis will indicate the directions that provide the greatest ability to distinguish the groups. And I've got 1 point for this. How do the MANOVA differences found above in the hypothesis test that we just did reveal themselves in the projections provided by the discriminant variables, and which discriminant variables are useful for detecting which differences? So let's just discuss this. I'm not going to do any typing, and I'll zoom out a little bit so we get this totally on the screen. That's good enough. All right, so looks like, let's start with canonical direction 1. So one idea here is to canonical direction 1 is, can you draw vertical lines that separate these groups? And absolutely you can. You can draw a vertical line to separate the red on the left from the green on the right. And you can draw a line pretty well that separates the green from the blue and purple. Now there's some overlap when you draw that vertical line, but just that one direction, it's a linear combination of all the isotope variables. That linear combination basically gives you a one-dimensional version that would result in the same conclusions, that the red is different from the green and everything else, green is different from everything else, and the blue and the purple have the same mean, right? Direction 2, canonical direction 2, it looks like canonical direction 2 is helpful for separating green from the other 3, right? So if this first one wasn't that good at discriminating some of the tail of green from blue and purple, now we might be able to get a little more ability to discriminate green from the others. And it looks like canonical 3 does nothing for us. So all the information's basically for the differences between these groups is contained in canonical direction 1 and 2, and effectively all of it in canonical direction 1. So we will discuss this type of analysis in much more detail in a later assignment, but I think the discussions that I just provided help you answer these two questions. So, okay, I think in addition to the multivariate analysis, a variance that we did, I believe that the other useful part of this assignment is this nested for loop for making pairs of categories. All right, hope that was helpful, and I'll see you in the next one.